Okay, so let's talk about shift matrices in relation to their nilpotent index and a little bit about them. So what is a shift matrix? A shift matrix is a matrix like this. So it has ones above the diagonal. On the first superdiagonal or the second superdiagonal, and everything else is zero. Now, the idea of those shift matrices is take a vector and literally shift its components, its terms. So, for example, if I take this shift matrix, you see zero everywhere and the superdiagonal one. So it just take a vector x1 and x4, and when I apply the matrix to the vector, it just shifted all the components one left, and on the right there is another new zero. So you can see that x1 just disappeared and everyone else just moved one slot to the left, let's call it. Okay, so what happens if I take to the power of 2? I mean, if I take a to the power of 2, it's still a shift matrix, and it just shift twice. So for the first shift, as we did before, we're getting from the vector x1, x2, x3, x4, this vector, just shift 1 to the left and add 1, 0 to the right. And when I apply again, I get a squared, and it's just a shift to the left twice. So x1 and x2 vanish, instead of them on the right side zeros, and x3 and x4 moved two slots to the left and override x1 and x2. So there is a general rule for a to the power of k until you're getting to the power of k. What do I mean by that? I mean by that in the end, if you do enough a to the power, you'll get just a zero vector, right? For example, for a to the power of 3, you'll get a4 here and everything else 0, but a to the power of 4 is just the zero vector, and a to the power of 4, as we will see for this a, which is 4 on 4 for a shift matrix, we will get a zero matrix. So here we get to the idea of the nilpotency of this shift matrix and its powers. So we start again with this shift matrix on one on the superdiagonal, and as we saw, just shift. And when we take a to the power of 2, the a is moved from this superdiagonal to the next superdiagonal, a to the power of 3. Again, next superdiagonal. Now you can guess what will happen when we take a to the power of 4. As we saw, it took a vector to be 0, and a to the power of 4 is really the zero matrix, so it's logical that it happens. So there is a general rule for an n on n shift matrix, as we saw. If you take this matrix to the power of its order, namely to the power of n, we'll get a zero matrix, as we saw. So, and this is the smallest, for this type of shift matrices, this is the smallest index that annihilates the matrix. So this is the nilpotent index by definition of this matrix. Just take the matrix to the power of its order, and therefore it's also the minimal monic polynomial that annihilates this matrix. So therefore you can conclude that this x to the power of n is the minimal polynomial of this shift matrix. And for a triangular matrix, if you remember, the eigenvalues are on the diagonal. So if you look on this matrix, the eigenvalues are just 0. So generally, we can say that the eigenvalues of a shift matrix are all zeros. Okay, so we talked a little bit about shift matrices, what they do, and how they change with raising it to the power, and what its nilpotent index is, and how it works, what it does to a vector, and what its powers they do to a vector. And you can also relate it to a Jordan form. You know, Jordan form is like this, or Jordan block if you want, where on the diagonal we have the eigenvalues, and the super diagonal we have ones or zeros, depends on the size of the block. And you can look on the Jordan form as this formula, like it's lambda I plus a nilpotent matrix. And here, when lambda is 0 in our case of shift matrix, you will only be left with the part of the nilpotent matrix of the Jordan form. Okay. And that's all I wanted to say about the shift matrices in relation to its nilpotency and nilpotent index, it was a little bit nice. Thank you very much. Thank you all. And that's it for now.